Okay. So maybe we can. I would like to start. So we had finished by having this new definition of the tangent space. So we had said that if X is a variety and P is an X, we had defined this tangent space of X at P to be the dual. So we have the Roper ring, the maximal ideal at P inside the Roper ring at P. And then we had defined the tangent space of X at P to be the dual space to NP modulo NP squared. And we also then, as last thing, had said what the differential of a map is. Now I want to just say a few more elementary things about this. So the first thing is, so by definition, so if I take this definition here, the expanded space of X at P depends only on a neighborhood of P in X. Now the Roper ring of P in X is the same as that in any open neighborhood. So, so in particular, if U subset X is open, we have therefore TP U is equal to TP X. In particular, this also holds, for instance, if X's are fine, so if and U X open, then TPU is equal to TPX in particular. So that means we can use this other definition that we had, for U. And so now if X is say quasi-projective, then we have that X has an open cover by affine varieties. No? And so then that means if P, so in particular we can, but we don't even have to say this, but anyway, so and then TP X is isomorphic, so to TP U, where U is one, maybe we call this UI. Well, maybe I don't want to call them UI because otherwise it seems BI. BI, where P is in BI. So therefore one can always assume that X lies in a so up to isomorphism, VI actually lies in some AN, and so in order to compute the tangent space, we can always assume we are in AN. So in particular, let me do this concretely. So X in Pn quasi-projective. So P is in X and follows there exists an I such that X that P in X, that P is in UI, which is the set of all Q in Pn, so Q equal to Q1 to 0 to Qn in Pn such that Qi is different from 0. No? So P will lie in one of these sets, and then follows that TPX is equal to TPX set to UI, which is isomorphic to tangent space of. So we have this. So if you want P of P, Pi of P, or Pi of X, no, it's the isomorphism exactly. So concretely, this means, and this map was just that we, we can put the we dehomogenize with respect to the ith coordinate. So we can always compute the dimension of the tangent space by just, looking, putting one of the variables equal to 1. So, so let me say this more concretely. So if if X in Pn is closed, the ideal of X, the homogeneous ideal of X, is generated by some elements F1 to Fm. But these are homogeneous polynomials in x1 to xn. And P is an element in X with say in X which lies in UI, so the ith coordinate is non-zero. Then TPX is equal to, is isomorphic to T whatever. How to put it? It's the same thing here. T Pi P I of I X, which is just the. So what is this? This is the zero set of F1 from x0, and the ith coordinate we put equal to 1. So then this thing, so maybe, so if I call Pi of, so this thing is some closed subset in An, so I write this y, which is just the zero set of F1 of x0. At the ith coordinate we have 1 until Fm of x0, 1 in the ith coordinate xn. So the image under this chart is just this affine algebraic set, and the tangent space to X is isomorphic to the tangent space at, if you want, Phi of P to Y, which is just the zero set of the differentials. So these are now viewed as polynomials of x0 to xn, that don't depend on 1. So maybe I should have given it another name to be on the safe side. I don't want to. So just write gi of x0 to xn with the out the xi is just defined to be fi. So g. Don't know why I'm so confused. Of x0 is here put 1. And so it's just the differential of these things. These are polynomials in x0 to xn which do not depend on xi. Anyway. So this will be, and so you see, you can just use the usual, the first definition that we had before to compute the tangent space of any projective right. So you just localize, you just go into one chart and look there. So let me look at one example to see that it's actually easy to compute. So it's not here. Example. Take the zero set of, say, so now, say, well, okay, let's say x0 x2 squared minus x1 to the 3 in B2. Okay, so we want to see whether this is, what are the singular points and so on of this. So we can look, so we have to look in the different charts where the singular points are. So when x0 is different from 0, I can put equal to 1. This equation becomes, we get the zero set of x2 squared minus x1 to the 3 in A2. And we see that, we already see that this is the cusp. The only singular point is when both x1 and x2 is equal to 0. So this is only singular point. In this chart is 0, 0. So that means this is the point 1, the point 1, 0, 0 in P2. And then let's when, say, which one do I want? When, say, which one do we want? When x2 is equal to 1, we get the zero set of, what is it, x0 minus x1 to the 3. We see this is actually non-singular, so this zero set is non-singular because the derivative by x0 is always, this is non-singular. And finally, we can look at the last chart. So when x1 is equal to 1, we look at the zero set of x0. What is it? So when we are assume we are when we are outside these two sets, so when both of these are 0, so when we are outside the union of them, so if x0 is equal to x2 to 1, then we see here we get 0, so this would force this to be 0, so it can't happen. So we get the zero set of x0, x2 squared minus x1 squared contains no points. So no points here. in particular, there can be no singular points. So thus we see the only singular point of this x is the point 1, 0, 0. Okay. So
what happens when we plug in x1 equals to 1?
Well, you can plug in x1 equal to 1, but anyway, here I'm just saying that there are no points, so it's not like that these are mutually exclusive, no? If I put, here I put this equal to 1, here put, which means, so when these two both don't hold, then I'm here, and so I mean, so there are no further points in the curve than those. But I can also plug in x1 equal to 1, so it's not necessary to find things, because what this means is that all the points when x1 is equal to 1 are already contained in these two charts. I mean, all the points which lie on the curve for which x1 is equal to 1 will lie either here or here. So we have already dealt with that. But I can look at the equation independently. So if x1 is equal to 1, so this is another chart, obviously the equation is 0 set of, what is it? It's 0, x2 squared minus I mean, I kind of purposefully didn't want to look at this one because it's a little more difficult to analyze. So you can see, so this looks like it's, you know, if you take the derivative of this, you get, so this should be equal to 1. x0 times x2 squared should be equal to 1. It still contains no singular point. Because in principle, if you take the derivative here, when x0 is equal to 0, then, so what are the, so the only point where this vanishes is when x0 and x2 is equal to 0. But no, when x0 or x2 is equal to 0, but then the product cannot be 1. So there's also no singular point here. No, because you always, it's not just about the differential being 0, but also you must be on the curve. So no. And indeed, what actually we have is when, so we have seen that x1 is equal to, okay, fine. So now we now want to show that for any variety, the set of non-singular points is open and dense. So we have shown this in the beginning for hypersurfaces in AN. Now we want to show it for any variety as a kind of consequence of this. So first, let me remind you of the Jacobian, so definition. So let's take some polynomials, f1 to fr, and some polynomials in n variables. So the Jacobian of these things is just the following, the usual matrix that you know, J of f1. So maybe I have to, for the moment I just do this, f1 fr, which is the matrix of the partial derivatives. Okay, so this is just a matrix whose coefficients are polynomials in our variables. Now, one should note, if I take differential at P of F1 if I take the differential at P of Fi and apply it, so let me see, how should I proceed? So let me just say, if I take, so I take the differential, at P of F1 until the differential at P of Fn of R. So this is a map from the tangent space, as a map of the tangent space of as a map from K to the so as a map from K to the N to K to the R, just A1 to AN is mapped to dF1 by dPFI of AI, and this for I equals 1 of dPFI of A, and this for I equals 1 to R. So we get this vector, we just apply the differential to this vector, this gives us a number, and so this gives us a map like this. Then note that this is this map.
Sorry, you have A1 to AR, or A of A1 to AN, but here on the right hand side you have only A.
Yeah, the whole A is equal to that.
Okay.
I actually don't need this, I need it in a moment. But an element A here is such an n tuple. And so, note that if I do this, if I take dPFI of A1 to AN, like this, of this A, this is just sum I equals J equals 1 to N, the partial derivative times xi applied to this A1 to N, so times AI. So that means this map here is a linear map given by the matrix. J F1 to Fr at P. I just have, if I put here, if I specialize this to P, and then I put here A1 to N, then I get coordinate-wise just this, just what is written here. So the Jacobian just gives me this set of differentials. And so, thus, in other words, in particular, if X in An is closed, and the ideal of X is equal to F1 to Fr, we have that TPX is just by definition, so this is the old definition of the TPX, but I kind of want to always identify that, is equal to the kernel of the Jacobian of F1 to Fr, Ft. No? So I can also express it like this. And this allows us to use some simple linear algebra. So now I want to state my thing. So I say, so theorem, let x be variety, then first the set of regular points of x is an open dense subset. So almost all the points are regular, so non-singular. And the second one is for all points P and X, we have the dimension of the tangent space of X at P is bigger or equal to the dimension of X. So a priori we had said the point is non-singular if and only if the dimension of the tangent space is equal to the dimension of X, but obviously if it's singular it could in theory have been sometimes smaller, sometimes bigger, but the statement is it's always bigger or equal, and when they are equal it's non-singular. This also means that if you wish to show that the point is non-singular, it's enough to show that the dimension of the tangent space is at most equal to the dimension of X. That can sometimes be an advantage. And we also see that almost all points are dense. So let's try to make it proof. So first we can reduce to the case that X is affine. So X has an open affine cover. Also that means it has a cover by open subsets which are themselves affine. And each Vi is isomorphic to a closed subvariety of some affine space. So we can assume, and obviously the dimension of X is equal to the dimension of Vi, because the dimension of a variety is the same, and if P lies in Vi, then the dimension of the tangent space is equal to that. So we see that both 1 and 2 are invariant under replacing X by Vi. So thus we can assume X is affine. This a priori means we can assume that X is isomorphic to a closed subvariety of An, but these statements are invariant under isomorphism, so we can assume that X is a closed subvariety of An. Okay, so this is the first thing. So so we put ourselves in this assumption. So we have the ideal of X, which is generated by some elements, where the Fi are some polynomials. Now we want to use this thing with the Jacobian. So then we know the tangent space P of X is equal to what I wrote to the kernel of the Jacobian of F1 to Fr at P. Now, with such a thing, the thing is always that if you just take the, so that means that the dimension of the tangent space will actually have something to do with the rank of this matrix. No? So, thus, the dimension of the tangent space at X is equal to n minus the rank of this Jacobi. And as usual, we have used this many times, the locus of the points P where the rank of a matrix of polynomials is smaller will always be a closed subset because it's a zero set of some minus. And so this will show that this will in particular then show that X rank is open. But let's look at it for a moment. So thus, for any number d, the set, so this is xd, which is the set of all points in X, such that the dimension of the tangent space of X is bigger or equal to d, is closed in X. No, because it's a zero locus of the n minus d times n minus d minus of the Jacobi.
So what is d?
For any d is a number. No, for any d, the number of points where the dimension of the tangent space is bigger than d is closed. That's the first step. Now we have to see what d can be. No, this is just because we have this matrix of polynomials. So if I take the minus, they are polynomials. We take the common zero locus of these polynomials. It is closed. No, the t for which it's zero. So now we want to see what the possible value of the g is. So choose the largest d for which xd is equal to x. Obviously, so the dimension of the tangent space is at most n, because we are in an. So if we take d equal to n, xn is equal to x. But what is the largest? The largest d or the smallest d?
Should be the largest.
Yeah, no, the other way around. So it's at most n, but I take the largest d for which is equal to x. So, for instance, if we put d equal to 0, then obviously the dimension of the tangent space is at least 0. So, and if we require the dimension of the tangent space to be larger and larger, at some point it will become empty. For instance, if we put d bigger than n, it will be empty because the dimension of the tangent space can be at most n. So then is the largest d for which xd is equal to x. So then, if I put x0 to be x minus this xd, minus xd plus 1, so xd plus 1 is no longer equal to x, and it's a closed subset, so this will be a non-empty open subset of x. And so also open and dense in X. So now we want to show that D is equal to the dimension of X, I claim then our theorem is proved. Because then, first,
But actually we have that every point in this set x0 is regular, right?
yeah, that follows also, yeah.
But it follows without this because every point here is by definition the dimension of every point in x node is such that dimension.
No, I mean, we just said that the dimension is the minimal of the possible dimensions. It's not. We don't know that the dimension of the tangent space is equal to the dimension. That we still have to prove.
Oh.
No, we just have. No, we just said it's the.
Sorry, the dimension. If we have a point in x node, therefore the tangent space is not of all of x, by definition.
No, not the tangent space is not all of x. The dimension of the tangent space is. What do you mean the tangent space is not all of x? The tangent space has nothing to do with. It's a subspace of an. So this has nothing to do with x. So I don't know what you mean.
The tangent is because if we have a point, it is not in xd plus 1.
Yeah, and so.
Being in xd plus 1 means the tangent space is greater than d. Therefore, the tangent space is less than or equal to d.
Yeah.
The dimension.
Yeah, that's true. Okay, that's all that we know. But I mean, we are almost there in spite of that, because we just have to see that that if we show the dimension of d, that d is equal to the dimension of x, then it follows that x0, that the points of x0 are non-singular, because d is the dimension of the tangent space for. So you know, all the points in x0 have precisely maybe I should have said it. By definition, if a point P lies in x0, then the dimension of the tangent space is precisely d, because it's so it's the smallest one for which so note for P in x0, we have that dimension of TPX is equal to D, no? By definition, because it is smaller than D plus 1, and D is the smallest number which can have. So we want to show the dimension that D is equal to the dimension of X. Then first we have that x0 is equal to x reg, which is open ends in x. No, because as I said, then the dimension of TPX is d, but now d is equal to the dimension of x, so we have that it's not a singular point. And second,
shouldn't it be less than or equal to d?
No, we want it to be equal to d, that's the point.
But what follows from the definition is that it is less than or equal to d.
No, it follows that it's equal to d, because d is we take the largest d, so that xd is equal to d. If we could, then we could take a smaller d. No, we take the largest d. So if we had the other inequality, we could replace by one smaller d, and so on. So it is precisely d. Okay. And finally, we have also, obviously, again by definition, that the dimension of TPX is bigger or equal to the dimension of x for all P in x, because we have, after all, this is what is written here. You know, D is the largest one, so that this is the case, so it means that for all points the dimension is bigger equal. Okay, so we have to only check this, and this we check by reducing to the case of hypersurfaces, where we have proven such a thing. So you know that x is birational to a hypersurface in defined space of dimension of x plus 1 that we prove. And we also know that if I take, so maybe this hypersurface I call y, that the regular locus in y is open and dense. Because you have shown that for, if I take a hypersurface in AN, then the non-singular locus is open and dense. This was one of the first things we showed. So choose an open subset of X, which is isomorphic to an open subset of Y. They are birational, so they have isomorphic open subsets. Then U intersected the regular locus, so maybe open subset, maybe I call this U of X, so go to an open subset V, then V intersected by rect is isomorphic. So a non-empty open subset. Of X, because the intersection of two non-empty open subsets is non-empty and open, and via the isomorphism this is also an open subset. And so, and the dimension and for P in this open subset, we have the dimension of tangent space P. And X is equal to the dimension of X. Namely, it's equal to the dimension first of Y, but the dimension of Y is equal to the dimension of dpx, so I could say dimension of Y equal to the dimension of X. And so we have an open subset, so maybe I call this also something, W. So we have an open subset W of X where the dimension of the tangent space is equal to the dimension of X. So that's also, if I take W intersected with X0, is a non-empty open subset. And thus D is equal to the dimension of X. Because for elements in X0, the dimension of the tangent space is D, and for W, for points in W, the dimension of the tangent space is the dimension of X.
Why is this intersection non-empty?
Because both are non-empty open subsets. Any two non-empty open subsets have non-empty, any non-empty open subset is dense. So certainly, okay. So this is the proof. I don't know, I seem to be a bit less, yeah, okay, anyway. I hope it was sufficiently clear, although it's in some sense, I think I could have explained it slightly better. Okay, so that's as much as I wanted to say generally about this. Now I wanted to look at the special applications for these two curves. So this actually is even slightly related to the talk of Forzi. But as at least you will notice. So the thing is that if you have a non-singular curve, so a non-singular point on the curve, then the local ring has a special property, which is that it's a discrete valuation ring, so we have a certain valuation on it. So basically, for a function in the local ring, you can say to what order it vanishes at that point. This, you can organize this in a nice way. And this leads to a certain non-Archimedean valuation on this ring, which is generalized by whatever was talking about. And so let's. And this is somehow, I mean, we won't have much time to talk about it, but it's fundamental for the actual geometric studies of curves. So it's most of the things one does in terms of this. So let me start with it. So let me just talk. So first, a curve for us is a variety of dimension 1. So variety means, and so we want to see, to show that, so if C is a curve, and P a point in C, a non-singular point, we have a particularly nice structure for the local ring. So we want to show that the local ring of O, C, and P is a discrete valuation. I have to first explain to you what that is. But first, before I even introduce this, I want to do some algebraic background. So let's do a bit of algebra. I will need Nakayama's lemma about local rings. So some notation. So if A is a ring, with M and E module, and say I an ideal in A, I want to use, so by IM, I denote, just what I get if I, just instead of multiplying elements in M by elements in E. So I take everything which I can obtain by multiplying an element in M by an element in I instead of by an A. So this is just the set, if that's correct, or Bm if B is in I and M is in M. And this is also an A model. This is because I is an ideal, so if I multiply this with an element in A, then the product will still, then I will still be in IM. If I take the sum of these two things, I will also still in IM because I is an ideal. So B1M plus B2M is B1 plus B2 times M and so on. This is an A module because I is an ideal.
I think it's not a module because, for example, if I have B1M1 plus B2M2. I mean, we take the
I think I made a mistake.
by this.
Let me see. Maybe I made a mistake, yeah. Well, okay. Maybe you're right, and I actually take the ideal generated by this. The module generated by this. Sorry. First make a big story why it's a model and then it isn't. But anyway, okay. So now we come to a kind of a fundamental lemma about local rings, which is Nakayama's lemma. It comes in, I mean, there are two different statements which are called Nakayama's lemmas. I which are called Nakayama's lemma. I will state them separately. The first one is the following: is somehow a criterion for a module to be 0. So let A be a local. So this is over local rings. A be a local ring. Remember, local ring means it has a unique maximal ideal which consists of all non-units with maximal ideal M. Unique maximal. Okay. And I take that M be a finitely generated A module. So every element can be written as a finite linear combination of elements, of finitely many elements in M with coefficients in A. So if M is equal to M times M, then it follows that M is the 0 module. So obviously, if I replace M by I times M, it somehow becomes smaller. But in theory, it could be, still stays the same. It looks like it becomes smaller, but you still can write all elements like this. But the claim is that this actually cannot happen for a finitely generated M module. So if I multiply with the maximal ideal, and it doesn't get smaller by doing this, then it was already 0. So the reason, okay. And we do need the assumption that M is finitely generated as a module, otherwise there would be counterexamples. So let's do this. It's a kind of a typical indirect argument, which is not very different from some others we have seen. So proof, we assume that M is not 0. And so we want to use that it's finitely generated, so we write down a set of generators. So we can find a finite set of generators, and then obviously once we can find such a set of generators, we can also find a minimal set of generators with the smallest possible number R. Because the number of generators is an integer, we can always find the smallest possibility. So we choose such a minimal set of generators. So now, basically, it's kind of clear if I set it up like this, that I want to show that if M is non-zero, then I can find a smaller set of generators than starting from minimal one, which is a contradiction. So we know that UR, so the last one, is an element in M, which is equal to M times M. So thus we can write it as a linear combination of the UI with elements in M. So you can write UR equal to sum I equals 1 to R Mi times UI, where Mi are elements in M. So we can bring the UR here to the other side. So we have follows that if I take 1 minus MR times UR, this is equal to the sum I equals 1 to R minus 1. mi ui. You can somehow see how this leads to a contradiction, because now it's easy to see. We see in a moment that this is a unit, so we can divide by it, and so we have expressed UR in terms of the other generators, which means we didn't need to UR. And so it was not a minimal set of generators. So, but so take 1 minus MR is a unit. Because we're in a local ring, if it was not a unit, then it would have to lie in the maximum ideal. We have that 1 minus MR lies in M, and thus 1 minus MR plus MR, so this would lie in M, and this would lie in M, also would lie in M. But this is equal to 1. And this is a contradiction, so otherwise 1 would lie in the maximum. So therefore this is a unit, therefore we can divide by it, so thus UR is equal to sum I equals 1 to R minus 1 Mi times 1 minus MR to the minus 1 times UR. So therefore already U1 to UR minus 1 generate M. As in not M. So it's a simple contradiction. You just have bring this on the other side, and you see that you need less generators. And so obviously, okay. So this shows that if you have a finite generate M module, a finite generate A module, and if it doesn't get smaller by multiplying by the maximum ideal, it was already 0. Okay, this was one statement, and as a corollary, we want to state what's often viewed as the second half of Nakayama's lemma, or sometimes just called Nakayama's lemma, namely a criterion for a set of elements in a module to be a set of generators. This is the following. Again, we are over a local ring. I can't even write corollary. Okay, corollary. So I get that A be a local ring. M, the maximal ideal. And large M, maybe I should have called it, anyway, in A module, finitely generate A module. So we assume we have some elements F1 to Fr in our module, such that their classes I write it F1 bar and Fr bar in M modulo M times M generate this M modulo M times M as a K vector space. I haven't told you who K is. where, you know, we have a so here I put where k is equal to a modulo m. No, this is the field. So if I, but not, so basically, so we have a set, some elements whose classes, after taking the quotient, generate the quotient module, then F1 to FR generate M as a module. So it's enough if these elements generated after dividing by the maximal ideal to generate the model. And you prove this by reducing it to the previous one. So we put N to be this module, no, so the idea generated by these elements, the module generated by these elements onto FR, so submodule and what we have to show is that M modulo N is equal to 0. No? So, to show no, that's what we have to show in order to show that they're equal. Okay. Note, if I take N modulo MM, this is equal to M modulo MM, which is equal just to the...
Why is M inside N?
Because the classes of the okay, do I actually need this? Maybe this is not. Let me write it differently to be on the safe side. Okay, then there's no doubt. So is the K vector space generated by these classes F1 bar into FR bar. That's what the assumption says, that this thing is generated by these classes of these elements. And if I take the idea generated by them, then this is precisely this. No?
Why just this equality hold?
Which one? This one?
Yes.
Because I said here that M modulo NM, MM, is generated by the classes modulo MM of these elements here, which is the same as saying that if I take I take the module generated by these and take it divided by M, this gives me this.
Yeah.
Okay. I know this must be a mistake. So, if I now take,
But now we can multiply this by m and we get 0.
yeah, that's basically the idea. Yeah, so let me try to do this. If I take m, but we want to consider, I'm just wondering whether I have this, if I take this here, I take m, a bit puzzled. Well, anyway, so I mean, so here I say this, but obviously I claim it follows that if I take n plus mm, this is equal to m, because here we have, we have added nm and divide by it, so then these are equal. So this is not, so the fact that this quotient is equal to this just means this, because every element can be written as a, we just have added the class value to divide. So therefore, so thus it follows if we take m times m modulo n, with the corresponding, this has an induced structure as a module, not just by multiplying by this. As this is equal to this, I can replace it. It's equal to m times n plus mn. Modulo n. Yeah. Let me just see. No. Which is just kind of confused. I really. Okay. I hate these kind of things, so let me see. I want to say, I multiply this. I want to say this is the same as n plus So what is the point? So maybe I can do a little bit, try to make it a bit more convincing. So what's that? So this thing can be written, if I make this intermediate step, so I say it's just the same as mm plus n modulo n. By definition, if I take, the model structure is that I have to multiply the elements here by elements in m, and to make the quotient, in order that the quotient makes sense, I have to add n to it. And so we have just this identity. And now we can use this, and this is just m modulo n. And so this shows that this model has a property that if I multiply it by m, it doesn't change. So it follows. Is equal to 0. M is equal to n. And so the ideal is indeed that this model is indeed generated by F1 to Fr. Okay, so that's the proof. Maybe Could have made it slightly clearer, but it is quite elementary when we just do these operations. We haven't worked so much with quotients doing these operations, but it's in some sense every step is kind of obvious. So anyway, this is the statement. So now we want to apply this to our situation. So we go back to our curve. So definition. Well, first we talk about this discrete. I have to define for you what a discrete variation is. So let A be a local ring, which is also an integral domain. So we have no zero divisors, and with maximal ideal M. So a discrete variation ring means that somehow the maximal ideal will be always a principal ideal, so generated by one element, and then also, in the suitable sense, all powers are generated by just the corresponding power of that element. So, let me write this out. So, A is called a discrete variation ring if first M is a principal ideal, then by ideal. That means I can write M equal to the ideal generated by T for some T and M. And such a T will then be called a uniformizing parameter. And secondly, so for any uniformizing parameter, T and any A in A, and we can write A to U times.
It should be non-zero. It should be non-zero.
Yeah. We can write this A as U times T to the N, otherwise it would obviously not be true. For U a unit in A, and no, N some non-negative integer. Okay, so every element, so there's one such thing which generates a maximal ideal, and every element in the ring, in this local ring, actually can be written as a power of such an element times a unit. So you can maybe check, this is almost trivial, but I can see whether you understand. So if A is a discrete variation ring, we'll always aggregate it like this. And T is uniformizing parameter. then if I take the maximum ideal to the n, this is just the ideal generated by t to the n. For all n. I mean, this is almost
I have a question. Do we require that such a form is unique, or we can prove it, or just?
No, it's not unique at all. What do you mean, how unique? Oh, that you can write A in unique way. So
Yes.
given t.
Yeah, given a t. For fixed t.
Well, I mean, that's kind of trivial, no? Because you have the, this is the unit. So you just have, in what sense unique? That the power is unique?
Yeah.
Well, that follows, no? It follows from this statement. Because if you look at it, it means if you write A equal to U times T to the N, it means it's in Mn but not in Mn plus 1. No? So, okay. So it follows A is equal to obviously that's a property of A. So therefore this n is determined by A. Also independent of what the uniformizing parameter is. So there would be more than one, it's just one possible generator. If I multiply t by any unit, it's still a uniformizing parameter by definition. And so, but this statement is independent. Time's almost up. Let me see that I can say something. So, well, I started a bit later. So this I need in the proof, but I do not want to. It's kind of easy, but if I want to say if X is a variety, and P is a point in X, then it follows that the local ring of X in P is an Euclidean ring. So let's see why this should be true. I will not, I just sketch it. So if X is a variety, obviously the local ring of X and P only depends on the neighborhood of P and X. So I can assume that X is affine, or is a closed subset of some affine space. And then you would want to take any ideal in this thing. And so what you can show is that if you take an ideal first, so X would lie in some En. So if I in K x1 to xn is an ideal, then I can look at the image of this in Ax. So then I, maybe I want to call it I, maybe the J to be not so confusing, and J plus the ideal of X divided by the ideal of X is an ideal in E of X, no? And the map from the ideals in kx1 to xn to the ideals in this thing is surjective. So you get all ideals in this way. In the same way, if you take now a point in X, and then you go to OXP, you can look at the, if you take an ideal in Ax, and you take its, the ideal generated by it in OXP, this will be an ideal here, and you can see that the map which associates to the ideals in AX, the ideals in OXP is surjective. So every ideal is kind of obtained eventually from an ideal in kx1 to xn. And all the ideals in kx1 to xn are finitely generated, and so the images of the generators will be the images of the generators here. So every ideal in OXP is finitely generated, therefore OXP is a Newtonian image. So that's the rough argument, but many details are missing to actually work it out. You would have to would be an exercise. So using this, I want to prove the following theorem. So let P be a non-singular point on a curve, and then the local ring is a discrete variation. So obviously we have to somehow, so we have to use that it's a non-singular point on the curve. So the curve has dimension 1, and the dimension of the tangent space is also 1. So let NP in OXP, OCP be the maximum ideal. We know that the tangent space of P at C, which is MP modulo MP squared dual, has dimension 1. So thus also MP mod MP squared is a one-dimensional K vector space. Let's take the generator of this space, or rather we choose an element T in MP such that the class of T in MP modulo MP squared generates this vector space. Then by Nakayama's lemma, we have that the maximum ideal MP is the ideal generated by T. That is, T is a uniformizing parameter. So this is not quite enough. So what we really now also need to see that if we take the intersection over all powers of MP, that this is 0. Because otherwise it could, so because we were implicitly this thing that every element can be written as u times t to the n, means there is that every element lies in m to the n minus m to the n plus 1. That means then that if you take the intersection of all the m to the n's, this is 0. And so let me first show, we want to show that m equal to the intersection over all n bigger than 0, m to the n, mp to the n is 0. So this we use again Nakayama's lemma. So obviously M is an ideal in OCP, and therefore also a module over it, which is Noetherian, So M is finitely generated as an ideal, and that means after all the same as being finitely generated as a model. Because the model structure is just that, isn't it? M is finitely generated. As a OCP model. And by definition, if I take MP times M, if I take the intersection over all MPs, MP to the n, if I multiply this by MP, I get the same thing. This is equal to M. So it follows that M is equal to 0. Thus, by Nakayama's lemma again, I mean by the other Nakayama's lemma, we have M is equal to 0. So, thus it follows. So there's no element which can lie in all positive powers. So every element, there is a last power. So if I take, it will lie in some power m to the n, but not in mn to the plus, in mn to the mn plus 1. So thus for every a in A, there exists an n such that A is an element in mp to the n, but not in mp to the n plus 1. Just means it's the largest n such that A lies in mp to the n. And there is a largest such because, okay, but then we can write A equal to U times D to the n, because if it like, okay, and this proof this. Maybe I will stop here. So this now gives us something which one could call evaluation on this local ring, namely the valuation of an element A in the local ring is if I write A equal times U times T to the n, the valuation is this number n. And you can think of that as the order of vanishing of A at the point P. And well, then we'll see how one proceed with this. Okay, thank you.